Have you ever wondered how an aimbot actually knows where to aim? Like, think about it. The computer has a player over here, an enemy over here, and somehow it needs to figure out the exact direction it needs to look. When I first started learning how this worked, I thought there was going to be some insanely complicated algorithm behind it. But the basic math is actually stuff you probably learned in school. We're talking coordinates, the Pythagorean theorem, and trigonometry. And by the end of this video, we're going to take two positions in a 3D world and calculate the yaw and pitch needed to face one from the other. First, we need to understand how positions work in a 3D game. In a normal 2D graph, we have x and y. But games are three-dimensional, so we need another axis. For this example, let's say x represents left and right, y represents forward and backward, and z represents height. Different games can use different coordinate systems, but the math we're learning is basically the same. Let's say our player is standing at 2, 3, 1, and our target is standing at 8, 11, 4. So now we know where both objects are. But knowing their positions isn't enough. We need to answer a different question. What direction is the target from us? And this is where something called delta comes in. If you've seen this triangle-looking symbol before, that's the Greek letter delta. In math, delta is commonly used to represent change or difference. So if I move from x equals 2 to x equals 8, my change in x is 8 minus 2 equals 6. For our two 3D positions, we can calculate three differences. Let's plug our numbers in. Our player's x is 2 and the target's x is 8. So, dx equals 8 minus 2, which gives us dx equals 6. For y, dy equals 11 minus 3. So, dy equals 8. And finally, dz equals 4 minus 1, which gives us dz equals 3. So now we have direction equals 6, 8, 3. This is extremely important. Instead of thinking about two completely separate positions, we now have a vector describing the difference between them. From our position, the target is 6 units away along x, 8 along y, and 3 units higher along z. And once we know that, we can start calculating angles. Before we calculate an angle, though, we need one more number. The horizontal distance to the target. For a second, completely ignore z. Imagine we're looking straight down at the map from above. Our x difference is 6. Our y difference is 8. And look at what we've accidentally created. A right triangle. So how do we calculate this diagonal? The Pythagorean theorem. Yeah, the thing everyone learns in math class and then asks, when am I ever going to use this? Well, apparently when you're trying to understand video game aiming. We know a equals 6 and b equals 8. So, 6 superscript 2 plus 8 superscript 2 equals c superscript 2. 6 squared is 36. 8 squared is 64. 36 plus 64 is equal to 100. So, c superscript 2 equals 100. Take the square root. c equals 10. Our horizontal distance is 10 units. In C++, that calculation would look something like this. We're literally doing the exact same equation. Square x, square y, add them together. Take the square root. Now we know how far away the target is horizontally, but we still don't know which way to look. That's where the trigonometry starts. If I'm facing forward and turn to my right, my yaw changes. Pitch is your up and down rotation. Let's start with yaw. Go back to our top-down triangle. We know the x difference. We know the y difference. What we want is this angle right here. If you remember SOHCAHTOA from trigonometry, tangent tells us tan, theta, equals opposite slash adjacent. But we're trying to find the angle itself. So we need the inverse tangent. You might know that as arctangent. Conceptually, we could write. But there's a problem. In programming, we usually have something better for this situation. And it's called atten2. Instead of only calculating atten dy slash dx, we can give atten2 both values individually. Why does that matter? Because direction matters. A target could be to our right. It could be to our left. It could be behind us. And the signs of x and y help tell us which region of the circle the target is actually in. atten2 uses that information to determine the appropriate angle. So our yaw calculation can start as float yaw equals atten2 dy dx. But if we print that number, there's something that might look weird. We're probably going to get radians. Most people think about rotations using degrees. A full circle is 360 degrees. Half a circle, 180 degrees. A quarter, 90 degrees. But programming math functions often work with radians. The important relationship is, so to convert radians into degrees, we multiply by 180 slash pi. That gives you s. Float yaw equals atten2 dy dx 180.0 f slash pi. Now we have our horizontal angle in degrees. One important thing here. Different games and engines define their axes and rotations differently. One game might consider this direction 0 degrees, while another considers a completely different direction 0. So if you've ever seen code adding something like 90 degrees to a yaw calculation, that isn't some universal aimbot equation. That's usually correcting for that particular coordinate system. The important math is the direction calculation itself. Okay, our yaw can point us left or right toward the target. But there's still a problem. What happens if the target is above us? We could be horizontally facing them perfectly while still looking straight ahead. That's why we need pitch. Remember earlier when we calculated dz equals 3. That means our target is 3 units higher than us. Now look at the situation from the side. The bottom of our triangle is the horizontal distance we calculated earlier. That's 10. The vertical side is our change in height. That's 3. And once again, we want this angle. So we can use at and 2 again. Except this time we're comparing height against horizontal distance. And that's our vertical angle. So now we have both pieces. And this is where everything finally comes together. Let's start from the beginning. We have our position. We have our target's position. First, subtract them. That gives us the direction from the player to the target. Then calculate our horizontal distance. Then calculate yaw. And finally pitch. That's it. We started with 2 points in 3D space. And using subtraction, the Pythagorean theorem, and trigonometry, we calculated the direction from one to the other. Now, this is the basic math. A complete aiming system can involve a lot more than these equations. For example, how do you choose between multiple targets? How do you determine whether something is inside your field of view? What happens when your angle goes from 359 degrees back to 0? How do different coordinate systems change the formulas? How do you smoothly rotate towards something instead of instantly snapping? And how would you visualize these vectors on screen? Those are all separate problems. But underneath them, the math we covered today is one of the core building blocks. If you want to see me actually turn this math into a visual C++ project where we can move a target around and watch the yaw, pitch, and vectors update in real time, that's what I want to cover next. Subscribe if you want to follow the series. And I'll see you in the next one.